Hello students, welcome back to our computer architecture class. In this session, we are starting unit 4, which is all about the control unit. Here, we will understand how control signals are generated and parallel processing through pipeline. You can find the notes for this topic is available in the description of this video. These are the contents of unit 4. Let's see them one by one. The first topic is called Basic Processing Unit. The main processing part of the computer is called Instruction Set Processor or simply a processor. It is a logical and functional unit of the computer that actually executes all the instructions given by the user or the program. Processor is also called Central Processing Unit. Usually, we refer to the Central Processing Unit or CPU that can be located in between the input and output unit. The CPU looks like this. It contains several components. One of the main part is motherboard, which holds the processor. But in the context of computer architecture, this processor is called CPU. We call it central because in earlier computers, it was the main unit that controlled all the computations in the system. However, in modern computers, there are multiple processors working together. So the term central processing unit is not always accurate today. Therefore, we now use the term instruction set processor or simply processor. The processor contains three important components. One is arithmetic and logic unit, control unit, and registers. These registers can be further divided into general purpose register as well as special purpose registers. Up to this point, we have discussed the first topic called basic processing unit. Now let's move on the next topic called ALU operations. In our syllabus, during the Unit 2, we study the topic called operational concept. The topics present in the Unit 4 actually an extension of this concept. If you want to revise the part, you can watch the video available in reading.com channel. The link is given in the description. I recommend you understanding this concept first before continuing the Unit 4 contents. In this concept, the core idea is about fetching the instruction and data. Fetching is nothing but bring the necessary details from RAM to processor. After that only processor start execution. This simple processor diagram comes from Unit 2. We already learned how these registers are involved during the execution of instruction. Similarly, in Unit 4, detailed processor diagram is there. We will now understand how the instructions are actually executed inside the processor step by step. In this detailed processor diagram, we will look at the same example we saw earlier in Unit 2 to understand it more clearly. So I will remove the old processor diagram and focus on this detailed processor along with this RAM content. Here, the different processor components can be connected through the single bus called internal processor bus. Initially, the program counter contains the starting address of the instruction. For this connection, there is a switch between the particular register and the internal bus. By default, these switches are disabled. Once the particular switch is enabled, then the data can be moved from internal bus to processor or processor to internal bus. In case of arithmetic and logic unit, the second input called B that can be directly connected to the internal processor bus. So once the data bring from the internal processor bus from any of the register that can be directly updated in this point. So first we take in the content from the program counter to internal bus that can be moved into the memory address register. Then the processor can read the content from the 0th location, and after reading that content can be moved into memory data register. Then this data can be moved into instruction register. This is called instruction fetch. During this period, select 4 control signal is enabled. So the constant 4 can be reached to A. Now these two values can be added. Result can be stored in the Z register. And this data can be moved to the internal bus, and also your program counter value is incremented. So this updation can be happened during the instruction fetch. When your processor start to execute this instruction, at that time your program counter point out the next instruction address. Now we are executing this instruction that instruction present in the 0th address. During the execution, your program counter always point out the next address of the instruction. You just recall the definition of the program counter. It is the special purpose register. It contains address of the next instruction. Let's assume the first instruction is executed successfully. Now the processor see the content of the program counter. That can be moved into the memory address register. Your processor read the content from this fourth location. That data can be loaded into the memory data register. That can be moved into the instruction register. During this instruction fetch, select 4 control signal is enabled. These two components are added and the results can be updated in the program counter. So during the execution of this instruction, your program counter point the next address of the instruction. In this way, your processor can execute the instructions one by one. Now we can see how these instructions can be decoded and executed. In this previous example, we already seen the register R2 contains the value called 10. After successful execution of this instruction, this value can be moved into R1. So now R1 and R2 having the value 15 and 10. That can be illustrated here. Now we will see how your processor going to execute this instruction. So R1, R2 contains the value. These values should be bring into the arithmetic and logic unit. So R1 value can be moved to the internal bus and also moved to the Y register. And your select control signal, select the second input that is called Y value that can be updated here. Then you can move the R2 register content to the internal bus. Now these two values can be added. The result can be moved into the R2 register. So in this way the instructions can be executed. So this is how ALU operations are carried out. Now let's look bit deeper and understand how the instructions are executed in our next concept called instruction execution. This operation is carried out using the switching mechanism that connects the internal bus with the corresponding register. Here, the program counter contains the bidirectional link as shown in this figure. So try to understand the different switching mechanisms present inside the processor and name of the control signal used. Whenever the data transfers from one register into another register, we should activate the output signal of the source register and enable the input signal of the destination register. I categorize the switching mechanism in 3 different ways. First one is unidirectional. The data can be transferred from only one direction. In this case, the data can be transferred in both the direction. In third case, the particular register can be connected to the internal bus as well as the external device called random access memory. So it has both input and output signal for the internal bus as well as the external device also. So that can be illustrated here. In the first case, there is only one connection. It is the input signal. The register name is Y. So the name of this signal is called Yin. Suppose the register name is R1 means the control signal name is R1 in. In the second case, it contains both the input as well as output. The register name is program counter. So the input signal is called PC in. The output signal is called PC out. In this case, the MDR register is connected to the internal bus. It contains input as well as output. Input signal is called MDR in, output signal is called MDR out. The same MDR can be connected into external bus that can be connected into your RAM. The input signal is called MDR in capital E and output signal is called MDR out capital E. This capital E represents MDR is connected to the external bus. So try to understand the different switching mechanisms present inside the processor and name of the control signals used. If you want to move the data from program counter into R0 register, you should activate the PC out and R0 in. This is the PC out connection in which the switching mechanism is there. The name of the switching mechanism is PC out. By default, it is disabled. When you enable this, you can move the data from program counter into internal bus. When you activate the R0 in, the data can be transferred from internal bus into R0. So the data can be moved in this way. In the same way, if you want to move the content from R0 into Y, you should activate the R0 out and Y in. So by enabling and disabling the control signals, we can move the data from one part into another part of the components present in the processor. Let's see how this switching mechanism can be worked. These two control signals can be connected to the control unit. By default, these values are 0. For this connection, 0 means it connects the 0th input to the register. This register made up of collection of flip-flops. The output can be connected to the 0th input. So the same output can be stored again to the register. That means the register retains the value. When control signals becomes 1, these 2 points are connected. That means what are the data present in the internal bus that can be stored into the register. For the output signal, by default it is 0. If it is 0, there is no connection. If it is 1, the connection can be made. That means the data present in the register can be moved into the internal bus. This output switch is made by tri-state logic circuit. This is the truth table for tri-state logic. If this control signal is 0, it produces high impedance. It means there is no connection. If the value is 1, it transfers the input data into the output part. So in this way, these switches are functioning. Now let's look at the complete set of control signals for a single instructions. They are shown here in this table. This represents the actual concepts of instruction execution that are discussed in this unit. To help you understand this clearly, I have added the necessary data in both the RAM and the processor registers. The example instruction is given as add within bracket R3, R1. Let's see how this instruction can be executed by means of this set of control signals. These contain 7 steps. For the first step, the control signal is PC out. PC out is nothing but the content present in the program counter that can be moved into the internal processor bus. The ALU B input is the open connection, so this data can be automatically updated here. The next control signal is MAR in, so the 500 can be updated here. When enabling the reading content, your processor can read the content from the random access memory in the address called 500. It takes some time. During this period, other controls can be executed. Select 4 can be enabled here. Then this 4 value can be moved into the first input of arithmetic and logic unit. 500 also is there. So these two values can be added by means of enabling the add control signal here. Now your arithmetic and logic unit can add these two values and store the result. Then we can enable the Z in connection, so the Z register updated as 504. In the second step, Z out can be enabled, so this data can be moved into the internal bus. So this is the open connection, so this is also updated automatically. Then PC in, this data can be updated here. The next control signal is Y in, so this can be updated as 504. Then we can move to the WMFC connection. MFC is nothing but memory function complete. Whenever we do the read or write operation, your processor can read the data or write the data from or to the RAM. It takes some time to read or write. So we have to wait for this. So this control signal is called wait for memory function complete. After successful read, it means the data can be moved into the MDR register. If this control signal is successfully completed, we can get the instruction present in the MDR. The next control signal is MDR out. So this value can be moved here and IR in. Then this value can be moved into instruction register. This is called instruction fetch. These three instructions are always for instruction fetch. So for any instruction, these three steps are followed. In fourth step, R3 out signal is enabled. Then R3 value, that is 1000, can be moved into internal processor bus. Then MAR in. Then we can start to read. So now your processor can read the value from the 1000th location, that is 10. It takes some time. During this R1 out, that means 5 value can be moved into the internal bus. Then Y in. Then 5 can be updated in Y register. Then wait for memory function complete. That means the data can be successfully read and stored into the MDR register. Now the MDR register is updated into 10. In next step, MDR out signal is enabled. So the 10 value can be moved into the internal bus. Then the next signal is select Y. So the Y signal is selected by this multiplexer. So the 5 value can be taken as the first input of arithmetic and logic unit. Then these two value can be added by enabling the add control signal here. The result is 15. Then that can be moved into the Z register by enabling the Z in control signal. In the next step, this 15 can be moved into the Z register to the internal processor bus. Then R1 input connection can be enabled, so the 15 can be moved into this location. So the instruction is successfully executed. Finally, it goes to the end state. Let's see the second example. We already know these three steps are followed for any kind of instructions. Then executing this particular instruction, we have to follow these control signals. So when you complete these three steps, we can get the changes in the processor like this. And now this instruction can be start to execute by your processor. So the control signal is R3 out, Y in and select Y. So the R3 value 10 can be moved here. Y in is enabled, so Y value is also updated and you can select Y. So this 10 value can be moved into the first input of ALU. So in the next step, R1 value can be moved to the internal bus. Then add signal is enabled. So these two values can be added and the result is moved into the Z register by means of enabling Z in control signal. Then Z out can be enabled and R1 input can be enabled. So the 15 can be moved into R1 register. Then finally your program comes to end state. So by varying the instructions given in the examination, you have to generate this kind of control signals. For this, you can follow these three steps for all the given instruction. Then depending upon the meaning, you can enable the appropriate control signals here. In the third example, you can try it your own. Here, these two values are indirectly specified. It contains only address. That address contains the separate values. You can try to generate control signals for this instruction. I hope you understand how the instruction is executed using these control signals generated by the control unit. In these examples, we just saw the set of control signal used for executing the normal instructions. Now let's see how the set of control signals generated for a branching instructions. For branching instruction, some extra controls can be included. I'm going to assume some primary values present in both the processor as well as RAM before going to explain this concept. And one more thing, branching instructions can be categorized into two. One is unconditional branch, another one is conditional branch. In unconditional branch, when you execute these instructions, the control can be moved without any condition. But in this case, depending upon the result, the execution control can be moved to the particular target or it follows the next address. So first we see unconditional branch instruction. So jump is the unconditional branch instruction. So once you execute, the execution control can be moved into the 1000th location. It is not execute the next instruction that is called 504. So when you execute this program during the fetching operation, the 4 can be enabled. These two value can be added as 504 that can be updated into program counter. During the execution, your program counter should point out the next address of the instruction, but it points the 504, but the actual next instruction present in 1000. So these two control signals also added for this unconditional branch instruction. Here, offset field of instruction register can be considered. So this offset value can be calculated by the difference between the address present in this instruction and the next address. So these two difference can be calculated and updated as the offset address. Here the offset address is 496. So this 496 can be read from the internal processor bus. Then add control signal can be enabled. So these two values can be added. The final value can be moved into the program counter. So the program counter now points to the correct address of the next instruction. In case of conditional branch instruction, let's take the example instruction as JE, that means jump equal into 1000 location. So it checks the condition. If it is true, then it move the execution to the 1000th location. If the condition is false, it executes the instruction present in the 504 location. So for that, we have to make some changes in this step. So this statement can be used here. So when you complete these 3 steps, you can get the changes like this. Now you find the offset value. Offset value is 496. For understanding this step, I focus this particular portion of the processor. In this control logic can be connected by means of some condition codes. Depending upon the condition code, the control signals can be varied. So when you execute this instruction, it compares the previous result condition codes. So in this previous execution, the condition codes can be set. If the value n set as 0 means it go into end. If the value 1 means it follow the step 5. So when you execute this fourth step, depending upon the previous condition codes, the n value becomes 0 or 1. So when you execute this fourth step, the offset value can be taken and is added with this 504. The new value 1000 can be calculated and the condition can be checked. If the condition is false, n value becomes 0. So it comes to end. That means the next instruction 504 instruction can be executed. Your processor always point to the 504 instruction. But suppose the condition is true, the n value becomes 1. It follow the fifth step. So when you execute this fifth step, the Z value can be moved here and updated into PC. Then the execution is completed. Now the program counter point out the next instruction going to execute. So in this way, the branching instructions can be executed by means of this collection of control signals. So up to this, we see how the control signals are generated for normal instruction as well as branching instructions. Now let's see how these control signals can be generated in multiple bus organization. Like the connection between these two topics, there is a connection between multiple bus organization with the unit 2 content called bus structures. In this unit, we studied about the bus structure like this. That means single wire can be connected to the different components of the processor. In multiple bus organization, different buses can be used to connect the various components of the processor. We already know the own advantage and disadvantage of these two structures. So we already know this single bus structure can be redrawn in detail in this diagram. In the same way, the multiple structure can be drawn like this. First, I try to compare the difference between this single bus and multi-bus architecture. Here the program counter can be connected with incrementer circuit. That means the program counter can be incremented automatically. It does not disturb the arithmetic and logic unit connection. Whereas in single bus architecture, during the fetch operation, your arithmetic and logic unit can be perform the updation process of the program counter. Here, the different registers can be connected like this. That can be denoted in the register file. In this register file, different general purpose registers are there that can be read the data from only from the bus C. The output can be moved into either bus A or bus B. And here the A and B bus are used as input bus, whereas C bus always used as the output bus. When we want to read the content from the program counter, we can enable the PC out. It only connected to the bus B. In the same way, if you want to read the content from R1 register, that can be present in this block that is called a register file. You can enable the R1 out. But this output can be connected both the bus A and bus B. So you can mention R1 out A. That means R1 register content can be moved into bus A. If you mention as R1 out B means the R1 register content can be moved into bus B. If you enable R1 in means the input is always taken from the bus C. The content present in the bus C that can be stored into the R1 register. If you want to move the data from these buses into bus C means then we can use the control signal called R equal to A. So whatever the content present in the bus A that can be moved into C. If you want to move the data from bus B into C means you can use R equal to B. I repeat again, R is nothing but the resultant bus. Here the resultant bus always bus C. Let's see how the instructions can be executed in this multibus architecture. The example instruction is add R4, R5, R6. First we understand the meaning for this instruction. The content present in the R4 register and content present in the R5 register both are added. Results can be stored in the R6 register. Let's assume the value is 5 and 10. The expected result is 15. that can be finally loaded into R6. And assume this instruction is present in your random access memory in the address called 500. So initially your program counter contains the starting address of your instruction. Now your execution can be started by means of this collection of control signals. When the first control signal is enabled, the content from the program counter can be moved into bus B. Then R equal to B means whatever the data present in the B bus, that can be moved into C bus. Now MAR in. So this value can be moved into MAR register. Then read operation can be activated. That means what are the value present in the 500 location, that is RAM location, the value is this instruction, that can be read. It takes some time, so during that time it increment the program counter. So program counter value incremented into next address of the instruction. Then you complete this instruction, you can successfully read the data and store into the MDR register. Now the instruction can be moved here. In the next instruction, this value can be taken to the bus B and R equal to B is enabled. So this value can be moved here. Then the input of the instruction register can be enabled. So now the instruction is filled. For these three steps in multiple bus organization using for the instruction fetch operation. In fourth step, the actual execution is carried out. Here R4 value can be taken into the bus A. So all the general purpose registers are present in this register file. R4 register content is 5 that can be moved into the bus A, and R5 content can be moved into bus B. Then in this multiplexer, A value can be selected. That means the 5 can be moved here. Then to enable the add control signal, these two values are added and moved into the bus C. Then R6 in can be opened in general purpose register that can be moved into R6 register. That means R6 value can be updated and the execution is completed now. So in this way, the control signals can be generated in multiple bus organization. Let's move to the next topic called generation of control signals, in which there are two methods are there. One is hardwired control, another one is microprogrammed control. So these set of control signals either be created by means of hardwired control or microprogrammed control. First see how these control signals can be generated by means of hardwired control. In this method, the control signals required to execute each instructions are generated using the flexible hardware circuit, such as decoders, encoders, and logic gates. In the left hand side, you can see the control sequence of the execution of the example instruction add within bracket R3, R1. Each step represents a specific set of micro operations that are activated at the each clock pulse. On the right hand side, we have the block diagram of hardwired control unit. It contains the clock, control step counter, and decoder encoder logic that can be connected along with instruction register, external inputs, and condition codes. The clock provides the timing signals to the step counter. It keeps the track of which step of the instructions can be currently executed, and the decoder generates the corresponding control signals for the particular step. Since all the control signals are produced directly by this hardware, this approach is fast, but it is also less flexible because any change in the instruction format we would require to modifying the hardware itself. In microprogrammed control, what are all the control signals present in this execution that can be noted as different columns. In the first step, identify what are the control signals are enabled. You make it as 1, remaining control signals are become 0. Then you can get this value for the first step. In the second step, these 4 values only enabled. So you can convert this 1 for these 4 signals only. Remaining signals are become 0. So this is the microprogrammed signal. So in this way, all the 7 steps, the microprogrammed instructions can be generated. So once this kind of instructions can be generated, your processor can easily identify which particular control signal should be enabled. So up to this, we studied about how control signals can be generated and understand how the complete instructions can be carried out by means of set of control signals in normal instructions, branching instructions, and multiple bus organization. That control signals can be generated either hardwired control or microprogrammed control. Let's we move to the next topic called pipelining. Before understanding this concept, let's see one real-time scenario. Just assume the election polling booth. This process contains different stages starting from verification and up to complete the voting process. And assume that each stage consume 1 minute. If a one voter can enter and leave, he can take 4 minutes. 20 minutes needed for completing 5 voters. I illustrate this in the timing diagram. After completing the first person, the second person can enter the 5th minute. At the end of 20th minute, 5 persons can be completed this process. This is called serial processing. When the first person leave the stage 1 into stage 2, at the moment second person can enter into the stage 1. In the next minute, the first person can move into the stage 3. The second person can move into the stage 2. The third person can enter into the stage 1. So at this 4th minute, all the 4 persons can be engaged in this process. So this parallel processing can be illustrated in this timing diagram. So now only 8 minutes taken to complete the 5 persons voting process. That can be compared in this way. So this parallel process save lot of time. In the same way, when executing the different instruction by the processor, that can be coordinated along with the different clock pulses. Each instruction cannot be executed in the single step. It typically follow the 4 steps. We already seen when you execute the instruction can follow these steps. So these 4 steps can be followed for any kind of instruction. So I illustrate here the first instruction can be subjected into fetch, decode, execute and write. After that, second instruction can be fetched, decode, execute and write. Then third instruction. So this is called serial processing. If you merge these instructions, you can get like this. So during the second stage of the first instruction, the second instruction is going to fetch. So when we compare this serial and parallel processing, in serial processing we need 12 clock pulses to complete the 3 instructions. Whereas in parallel processing, only 6 clock pulses needed to complete the execution of 3 instructions. So it looks like the water droplets flow inside the pipeline. So this concept is named as pipelining process. Here the instructions are overlapped. So let's we define what is pipelining. So it is nothing but overlapping the instruction execution so that we can increase the performance of the processor. So for the particular instance, more than one instructions can be executed by the processor. To achieve this, we have to include some extra mechanism called buffer registers that can be present in all the stages to manage this parallel processing. The advantage of pipeline is it increases the throughput. So the overall processor performance is increased. To design such a parallel processing architecture, it's somewhat complex. That is one of the disadvantages of pipelining. Another disadvantage is hazard. Let's we see what is hazard in next upcoming slides. When the write operation complete in the first instruction, then only the write operation of the second instruction is started. In some situation, the write operation can takes more time to complete this. After that only, the second instruction is going to write. So up to this, second instruction can wait for particular time. That is called hazard. So hazard is a situation that stops the execution of the parallel processing. For this situation, your parallel processing is stopped at particular time. So when hazard happens, the overall performance of the processor can be reduced. There are 3 types of hazard. One is data hazard, another one is instruction or control hazard, and last one is structure hazard. The hazard can be happened due to the data. Then it is called data hazard. When 2 consecutive instructions can access the same location, then parallel processing gives wrong result. Then we should follow the serial processing. Let's see these 2 examples. In the first one, if the value a equal to 7 means 7 plus 3 10, 10 into 4 40, b value becomes 40. But if we execute in the pipelined architecture, it becomes 28. Why? Because if your processor executing this instruction, the second instruction is already fetched. But after successfully completing this instruction only, a value can be updated as 10. So the 7 can be multiplied with 4, so we can get the result as 28. So this is the wrong result due to the parallel processing. In the second case, if you assume the c value is 4, a value becomes 20 and b value becomes 24. If you execute these two instructions parallelly, this result cannot be changed. The reason is these two instructions are data dependent instruction. In these two instructions, there is no data dependency. So when your processor execute this kind of instruction, you should be wait for some time, then execute the second instruction. So this kind of delay can be happened due to the data. So this hazard is called data hazard. Then we will see how to solve this data hazard. It can be achieved by two ways, by means of hardware, by means of software. When we use these kind of changes in hardware, we can handle the data hazard. Here, the output of the ALU can be connected to the one of the input of the ALU. So no need to wait for the writing operation. So during the execution, the updated data can be fetched into the one of the input of the second instruction. So here we are forwarding the operand to the input of the ALU. So this is called operand forwarding. This diagram can be logically denoted like this. So after this ALU result, the result can be taken in one of the input of the ALU. We already know this architecture. You just visualize this kind of connection can be made. Without this connection, the result can be moved into Z register and the particular output register. Then it can be taken again and do the arithmetic and logic operation. But by taking the result immediately, we cannot wait more number of times. So in this hardware method, we can handle the data hazard. This data hazard also handled by software. By introducing the no operation signals in between the data dependent instructions, your processor can wait particular number of time and avoid the data hazard. The second type of hazard is called instruction or control hazard. The time delay can be happened by means of instruction. Then it is called control or instruction hazard. It can be happened either branch instructions or catch miss. We already know for the execution of the branching instruction during the fetching operation, your program counter incremented into 504. But actual the next instruction is 1000. But in parallel instruction, the next instruction can be fetched. So in branch instruction, there is a need for some delay. So such a situation is called control hazard. Control hazard can also created by means of cache memory. In cache memory system, it is a small memory. It contains the frequently used data and instructions that can be present in between main memory and processor. Your processor first see the data present in the cache memory, otherwise it read the content from the main memory. The data transfer between processor and cache memory is too fast compared to main memory. If the necessary instruction is not available in this cache, that is called cache miss. If cache miss is happened, processor can take extra time to read the instruction from the main memory. So the control hazard can also happen by means of cache miss. That can be handled by instruction queue. We can store the collection of instructions instead of reading one by one from the main memory. So the delay can be avoided by this mechanism. The next hazard is called structure hazard. It is nothing but the hazard can be happened by means of external resources. The resources may be memory registers or input and output unit. When the two successive instructions can access the same resource, at that time, the second instruction should be wait for some time. This is due to the resources access. This kind of hazard is called structural hazard. And during these hazards, the side effects can be happened. Side effect is nothing but some additional changes can be made when executing the instructions. That additional changes can be either changing the registers or updating the flag or modifying some memory content. We cannot mention these changes explicitly, but these changes can be happened immediately when executing the instruction. For example, when we execute the conditional branch instruction like this, it also checks the condition codes that can be set by the previous instructions. It can take some time. So this is called one of the side effect. So we already seen in the branch instruction, this instruction depends upon the condition codes that can be generated by the previous instructions already executed. So this is called side effect. That condition codes can be also needed for different situations, particularly when executing looping and conditional statements. And for this instruction, these two operands also expects the carry. The carry can be generated here. So when executing this instruction, apart from these two values, your processor need to read the carry value that already set by the previous instruction. So this is called side effect. When handling the stack operation, when you push or pop, we also increment or decrement the top pointer. So this is our actual operation. Along with this operation also can be carried out. So this is one kind of side effect. So up to this, we have seen what is pipelining and what are the issues can be happened in the pipelining and how it is resolved. Let's move to the last topic called influence on instruction set. When designing instruction sets, we often make changes to the instruction to achieve better pipeline performance. While designing the instructions and addressing modes, we must also consider hazards and how they affect pipelining. The goal is to make sure the instructions are easy to execute efficiently and safely in a pipeline without causing too many stalls or conflicts during the execution. And these are all the examples for modifying the instruction set. When we are using the register to register addressing mode, the performance becomes faster compared to reading and writing data using the random access memory. So we can modify our instruction set to become only the register to register instructions. We also do some changes in modification in a hardware like operand forwarding. We can get the immediate result to avoid the data dependency during the data hazard. When we do the better mechanism to predict the branching addresses, we can avoid the delay. That can be helpful for control or instruction hazards. And the side effects can cause the performance for your pipelining process. To avoid this, we can explicitly use the condition code operations that can be incorporated in your instruction. For these methods, we can avoid or minimize the side effects. So that's all for today's session on Unit 4 Control Unit. We have understand how the processor works internally, how instructions are fetched and executed, and the important role for the control unit in coordinating all these operations. I hope this explanation helped you understand this concept clearly. The notes for this unit are available in the description below. You can download and go through them for better understanding. Thank you.